This video is part of CAE Associates Ansys e-learning series. CAE Associates is an engineering consulting firm in Middlebury, Connecticut, specializing in finite element analysis and computational fluid dynamics. We have been an Ansys channel partner since 1985 and have developed our Ansys e-learning series to help you maximize your software investment. Please visit our website, which includes an extensive resource library with over 250 items and counting in an easily searchable area. We also invite you to visit our Engineering Advantage blog, where we share insights from our many years of performing engineering analysis. CAE Associates also offers an extensive schedule of Ansys courses taught at our Middlebury office. If you need help deciding on the best courses to take for your application, visit our CAE University page. The complete library of e-learning recordings is available for viewing in our resource library and also on our YouTube channel at youtube.com/CAEAI.
Okay, so let's get started. Let me open up our my PowerPoint here, make sure we're looking at the right thing. So what we're going to go over today is Ansys Workbench Meshing, and specifically solid meshing within Ansys Workbench. And so the topics that I plan on covering, first and foremost, why do I want a brick mesh? So if you're in Workbench Meshing, you're creating a solid elements, why would you want to generate a brick mesh? And second, once I convince you that that's exactly what you want to do, how are you going to go ahead and do that in Ansys Workbench Meshing? So we'll show you the couple of different methods that are used in order to create bricks. And finally, I'll do a live demonstration on a part that I'll show you how I go about, my method for going about creating brick elements using Workbench Meshing. Okay. So how do I get a brick mesh? And before we even get to that, why do I want a brick mesh? Well, the reason that you want a brick mesh comes from basically the shapes of the elements. So 3D solid elements generally come in a few basic shapes. We have our hex element all the way on the left here. We have pentahedrons, which are wedges, prisms, or degenerate bricks. And we have tetrahedrons, which we can see all the way on the right. Now, using tetrahedrons is very easy. Most meshing modules will have, very easy inputs to create a tet mesh, and you can generally create fill any arbitrary volume with tetrahedrons with very limited user input and difficulty. Now, we also have pyramids. These are less common, but anytime we have a mix of tets and bricks, then we're going to need to also have pyramids to transition from one shape to the other. So of these four shapes, why is it that we want to use hex elements predominantly? Well, one of the major reasons is that hexahedrons can fill a given volume, so any arbitrary part that you may be analyzing, more efficiently than the other mesh shapes. So if we think about it, it takes approximately 5 to 6 tet elements to fill one brick. And the result of that is if we have more elements, then we have more nodes. If we have more nodes, then we have more degrees of freedom that we have to solve for. And that means our solution time is going to take longer with tet elements. For the same resolution of our solution fields, our degree of freedom fields, we're going to have to take significantly more computational expense using tet elements than we would with hex. Now, another reason we would like to use hex elements is that they're generally more uniform, and we can control the element distribution on a finer level. So for hex meshing methods, we often have a much greater control over, let's say, the number of elements in a certain span, how those elements grow and vary. So there's a lot of different control that the brick elements afford us. So now that I've convinced you that brick elements are the best thing going, what steps do you need to take in order to generate a brick mesh? Now, the unfortunate truth is that brick meshes always take more man time than tetrahedral meshes. It does take user input. So on the pre-processing end, you'll have to certainly give a little more effort. But hopefully, if you're doing anything that's computationally intensive, it'll save you some time on the solution phase. So brick meshes are usually created using one or more of the following approaches. First, we take our arbitrary part and we slice and dice. So basically what we're doing is subdividing our geometry so that we create 6-faced volumes that we can then use a sweep method to create brick meshes within. So for those 6-faced volumes, we create a 2D mesh of quadrilaterals and sweep them from one side of the volume to the other. And operations like this include revolving the mesh about an axis, like we see down here, sweeping the mesh along one or more curves, or sweeping from one face to another in a topologically similar fashion. I know these are all covered under the sweep method in Workbench Meshing, but there are also other methods that can create bricks, and these are more advanced algorithms, for instance, the multi-zone method. And we'll show you that in a little bit. So if you're not convinced yet that brick meshing is what you want to do, let's consider the part that we have shown on the screen here. Now, we have a generic part here that's not sweepable in its present form. If you see, we don't have a single source and a single target face and a smooth path between the two. So we're not going to, by default, be able to create a brick mesh with the sweep method. However, with a little bit of effort by the user, we can create a very uniform, controlled brick mesh. So let's take a look at that. What you see here is I've gone back from Workbench Meshing into Design Modeler and created a number of slices and formed those resulting bodies into a multi-body part. So now we have a collection of sweepable bodies, and you see that we get a very nice uniform mesh. The restriction that I've put on this mesh is that we have 3 elements to the thickness of the thin walls. Again, an arbitrary constraint, but it is something that I use in this instance to show that you can control this. It can be anywhere from 1 to as many as you'd like. And the result that we get here is a higher order mesh that we have 8,000 elements and a little more than 42,000 nodes. So it's pretty good. I mean, if we look each of these bodies with different colors or the individual bodies, we have a continuous mesh through the whole thing. And we have a pretty efficient mesh that we've generated. Now, if we take a look alternatively at our options for just going ahead and tet meshing this body without doing any of the work to get a brick mesh, what would our result be there? For the same resolution using tetrahedron elements, again, we're enforcing that we need to have 3 elements to the thickness of the thin walls. I was able to create this mesh with very little effort. So I didn't have to do really anything. I just had to wait for the mesher to do its work. So it's rather easy on my end. But the result of that is that now I have 84,000 elements and over 130,000 nodes. So I get 3 times the number of nodes, and obviously that's going to influence the computational expense. So I think right here we can see the benefits of taking that extra little effort on the pre-processing end to maybe do a little slicing and dicing and create a brick mesh. Okay, so at this point what I'd like to do is take a brief pause and open up our first poll. And that poll is going to be on the percentage of time that everyone spends doing their meshing during a particular analysis. So we'd certainly appreciate your feedback here. And let me just open that up, and we'll take a minute to get everybody to contribute. Okay, looks like we have a couple people that are just finishing up now. All right, it looks like almost everybody's participated, so we certainly appreciate that. And let me just wrap this up here, and we can open the results. And kind of what I would expect is that it looks like you guys are spending usually a rather significant amount of time during your meshing. Certainly that's an important part of the analysis process, and will be important, for you guys to make sure that you concentrate on doing that efficiently, creating brick elements. Let me just make sure I save this, and we'll continue on here. Let me go back to sharing my desktop. And okay, so now that you see the benefit of a brick mesh, you're probably wondering, how do I go about getting that brick mesh in Workbench? And there are several different methods that we can use within Workbench Meshing in order to create a brick mesh. We have the sweep method, the hex dominant, and the multi-zone, and certainly it's important to understand that each of these has different geometry requirements. So let's make sure we know that, and it's important to understand that so we know how they behave. And finally, what if I can't get a mesh that's entirely bricks? A lot of times for any part that you guys are analyzing, I'm sure most of you are not just analyzing bricks, otherwise you wouldn't be really breaking too much ground. So for any arbitrary complicated part, we may not be able to fill it entirely with bricks. So what we're going to try to do is fill it as much as we can with bricks, and then fill in the rest with tets. And that's where techniques called selective meshing come in, where we can control the mesh on a fine level on a body-by-body basis. Okay, so for the sweep method, the requirements here are that we have a topologically consistent source and target face. And what that means is that we have the same number of vertices per face with a smooth path from the source to the target. So if we take a look back at our part here, we can look at the bottom cylindrical face here, and we see we can sweep from this outer radius to the inner because we have exactly the same topology on both faces, and we have a smooth path from one to the other. Now, the sweep mesh is the default Workbench meshing approach, so it'll automatically try to mesh any bodies with bricks if it fits the topological requirements, and if it can't, if it doesn't fit those requirements, then it'll just fill it with tetrahedron elements. Now, even though this is the default, there may be instances where we want to go ahead and insert a sweep method manually. And the reasons that we may want to do that are to specify the manual source and target faces. So do that in a manual fashion rather than having Workbench detect them automatically. Some instances where that may occur: if you have more than one possible sweep direction and you want to control the mesh in a specific manner. If you want to sweep a mesh as a thin solid, so it only has one single element through the thickness, certainly a manual method will let you do that. Or if you want to inflate the mesh near the surface of the geometry, let's say, for instance, you have a stress concentration, that can certainly be useful for bunching elements in those particular areas. Now, another control that this affords us by manually specifying the sweep method is that we can set the number of elements in the sweep direction as well as a bias. So we can cluster elements in certain areas and set exactly the control we want over the generation of the brick elements. So a very powerful technique here, but does require a specific type of geometry to be present, and that's where the slicing and dicing comes in. Now, our more automated methods, the first of which is the Hex Dominant Method, don't require the slicing and dicing, and are kind of doing the same thing to create bricks, but in a behind-the-scenes fashion. So what the Hex Dominant Method does is creates a primarily quadrilateral mesh on this outer surface topology, and then sweeps that inward. So it'll try to create as many hex elements as possible, and then internally fill those areas where it can't create hex elements with wedges, pyramids, and tet elements. Now, the Hex Dominant Method is particularly useful for bodies that we have high volume to surface area ratio. So if you have big, chunky parts where you have a lot of interior volume, the Hex Dominant Method will be particularly useful. It won't be as useful for thin, sculpted parts just because of the nature of the algorithm. Now, once we use the Hex Dominant method, a neat little trick that we can do is come down into, if we highlight mesh in the outline tree and come down to the bottom of the details pane, you see we have the statistics. And if we list, let's say, the element quality mesh metric, we can see what types and roughly how many elements of each shape are created. So it just gives you a guide as to how many bricks you're creating and how efficient the Hex Dominant method is behaving. If you want a more detailed look at that, you can always go into FE Modeler. Now, our last method is the multi-zone method. The multi-zone method, and we'll show you this during our live demo, is an advanced algorithm that uses the hexablocking method, courtesy of ISOM, and that internally tries to do the slicing and dicing that you'd otherwise manually do in Design Modeler. So it'll try to create, based on the geometry, regions where it has topologically consistent pieces, and it can create brick elements by doing a sweep. So a very powerful method here, and we'll show you how that works in our demo. Now, the great thing about Workbench Meshing is that we have so many different meshing algorithms and meshing methods, and we can combine those in any manner that we see fit. So for a given multi-body part where we want a continuous mesh, we can combine any different number of meshing methods. You can see in this one we have a sweep method on this top hook region. We have a multi-zone on the bottom plate region, and then we have a tetrahedron method in the middle chunk there where we're not able to generate bricks. So we can interchange all these different methods for a multi-body part, without any difficulty to create the most efficient and highest fidelity mesh possible. Now, one last thing that I wanted to note on Workbench Meshing before we go to the demo is a feature called Selective Meshing. Now, Selective Meshing for multi-body parts allows us to dictate the order in which the mesh gets generated. So in this particular multi-body part, we have 4 bodies. And what we can do is say that, instruct the mesher that we want to mesh this base plate first, and then maybe the outer ring, and finally the hook before we go ahead and create the tetrahedron elements. So you can use the existing mesh that you've manually told Workbench Meshing to generate to influence the mesh that's going to be generated next. So a very powerful tool here. The way that we do this is by right-clicking on bodies and say generating mesh on that particular body. And if you're going to do any parametric studies, you can also record the order in which you mesh the different bodies. So that'll be persistent when you do any parametric updates. Now, this was introduced in version 13 and was called direct meshing in version 13, but is now called selective meshing in version 14. So a little bit of a name change, but the same idea, and has been available since then. Okay, so at this point, let's take another brief pause and do our next poll. We'd like to get some input on how many of you are using Workbench Meshing versus maybe some other tools or mechanical APDL. So let me go ahead and open that one up, and we'll get your input over the next minute or so, and we certainly appreciate that. Okay, looks like most folks have finished that up. Just another couple people. And looks like we're all wrapped up there, so let me finish that. Make sure we show that to everybody. So it looks like a lot of, a few people are using Workbench, maybe 50% of you, and we have some people using APDL. So certainly, hopefully, we can kind of show you the benefits here, and the ease of use of Workbench Meshing. Let me just make sure I save these results here. And let's go move on now to the live demo portion here. Let me share my desktop again. So let's go take a look now into Design Modeler. We have this part we see in Design Modeler where it's a big hook part with a base plate, and what we can see is that this is not in its current state ready to be brick mesh. So we can't just sweep it. We'll have to either use one of the advanced algorithms or use do some slicing and dicing to create a brick mesh. Now, one of the things I like to point out here is that if you're unsure, or if you think maybe something is sweepable, and you're not sure whether or not it is, a really neat feature in Workbench Meshing is we can right-click on Mesh, and we can go to the Show submenu and say Show Sweepable Bodies. And we see here, in this instance, nothing gets highlighted because we don't have any sweepable bodies. But in the event that we do, and I'll show you this shortly, what Workbench Meshing module will do is highlight any bodies that are sweepable in green. So it's a really easy visual cue to see if you do have sweepable bodies. And often this is important, particularly if you have complicated CAD parts where you're slicing and dicing and you may have small features that you miss. Ultimately, it's more important that Workbench Meshing thinks it's sweepable rather than you, and it can help you diagnose where you have difficult geometry. So let's go back to Design Modeler, and what I'd like to do is show everybody how I would go about creating a brick mesh with this part. Now, what I'd like to preface this with is creating a brick mesh and doing this slicing dicing technique is very much a personal approach to how you would decompose geometry. So if I gave this part to 5 different people, I could almost guarantee that I'd get 5 different geometry subdivisions and 5 different meshes in the end. So there's no right way, but what I'll try to do today is show you guys how I would go about doing this, and hopefully give you some clues into the process that I go through. So the first thing that I want to do is, this part is pretty clearly symmetric. So what I'd like to do is cut it in half, and we'll say for argument's sake that this is going to be symmetric loading as well. So what I'll do is first create a plane here, and I'll create it from this face so that I can just offset it, so it's in the middle of the hook there. And what I'll do is I already measured this, so I know the difference here. 0.375. And let me just flip the Z there. Okay, so now I have this plane right in the middle of the hook. And what I'm going to do is go to the Tools menu and create a Symmetry Object. Now, the Symmetry Object serves 2 functions here. One, it's going to use this plane, the plane 9 that I just created, in order to cut the model right in half. Now, it's also, once we go back into mechanical, going to allow me to, it's going to automatically apply the appropriate symmetry conditions. So it's a really powerful tool here, something that hopefully everybody's aware of. And once I generate this, you'll see now I've got my half of a model, and once we go to mechanical, you'll see those boundary conditions. Now, the first step in my slicing and dicing, what I'm going to do is separate this base plate from the chunky hook region. So the way that I'm going to do that is select these edges here, right around the joint, the area in which the base plate meets the hook region, and I'm going to highlight those edges and then go to the extrude operation. So if I use those edges as the base object in my extrude, I can create a slice, and what I want to do here is slice down through the base plate. So I select this edge that represents the correct vector along which I want to slice those edges, and I want to make sure I slice that all the way through. So now that when I generate, you see that I have 2 different parts here. So this slice in particular doesn't get me all the way to having sweepable bodies, but what it does is creates it sets me up for my next slice, which will then create 2 additional sweepable bodies. So it's kind of a preliminary slice. So the next thing I want to do is slice again through the base plate and cut off this rounded edge region. So what I do is select one of these edges, and an easy trick here is that I can extend my selection, in this case to the limits, and that'll select for me all 5 edges along this fillet on the edge here, which I can then use as the base object for another extrusion. So I change this over to a slice. Again, I want to slice down through the base plate and make sure that goes all the way through. And when I generate, now you see I have 3 bodies in my model. And on the base plate, I now have 2 sweepable bodies. So this one, the main area here, is very clearly sweepable, where I have a top face and a bottom face that look that are topologically exactly the same. Now this body on the outside, however, may be a little misleading. It may not look exactly like it's sweepable. But what it is actually sweepable, because I have the same face here as I do on the other end down here, and I can sweep it all the way around the outside. So it's definitely, definitely 2 sweepable bodies here, but I still have this chunky part up here that's not quite sweepable yet. So what I'm going to do is create one more slice, and I'm going to select this edge here. And what I want to do is use that as a base object for a slice. And this time I'm going to sweep it out along the Z direction and make sure it goes through that entire hook geometry. So now I have 3 sweepable bodies, and I have one last little body that's not really sweepable. Maybe I could create some more cuts, but for the purpose of this demonstration, this will suffice to show what we're getting after. Now the last thing that I want to do is make sure that I form all of these 4 bodies into a multi-body part. So I want to select them all, right-click, and say Form New Part. And that's going to ensure that once I go over to Workbench Meshing, that I get a continuous mesh through all 4 of these bodies. So if I go back to the project page, bring that over, and I right-click on the model and refresh to read in the new geometry, you see I get updated so that I have the same geometry and meshing that I have in Design Modeler. Now I have the symmetry conditions on this region here where I use the symmetry tool. My geometry shows I have a multi-body part. And if I right-click on meshing, it shows me exactly what I thought when I was doing the slicing. I have 3 sweepable bodies. So let me just right-click and generate the mesh, and you'll see the automatic method, real quick, will go through and sweep the bodies that it can, and then fill in meshes everywhere else. And what you see is I get a really nice, uniform, swept brick mesh with really very limited effort. So that took me maybe all of 2 or 3 minutes to do those slices. So really not a whole lot of effort. And from here, what I could do is go ahead and insert any type of different controls to get even more local refinement to tailor my mesh. Okay, so at this point, let's take a brief pause and do our last poll. And the last poll is going to be a little information on how we how you guys are experiencing meshing. What's your biggest bottleneck? So we'd like to get some feedback there. Just to note, looks like we are going to run over just by a few minutes, but hopefully you can stick around and see us do the multi-zone meshing. So let me open up this poll here, and let's try to get some of your feedback. Okay, looks like most of you have participated. Got a few people wrapping up here. See if we can get your input. That's a couple more seconds. Okay, great. So it looks like we have a wide array of different concerns here in terms of what's holding everybody up, and that's kind of to be expected. There are a lot of things that go into meshing. It kind of depends on what type of geometry you're using. But certainly, hopefully, learning a little more about the Workbench Meshing tool should help you guys out. Okay, so the last thing that I want to show you before we wrap up the webinar for today is the multi-zone mesh method. So if I bring that over into our screen here, what you can see I've done is suppressed all of the extrude operations, so I got rid of all the slicing and dicing that I did, but I did retain the symmetry just for to make it a little smaller. So if I want to create a multi-zone mesh, what I do is I right-click on the mesh folder, insert a method, and scope it to the appropriate body. And I go ahead and change that method to multi-zone. What you'll see is I get a number of different options under multi-zone. Now, the map mesh type dictates what type of mesh it's going to try to map over the surface of the body. And the free mesh type is going to be what type of elements it's going to create on the interior. So if you set free mesh to not allowed, basically what that's going to do is make the meshing method fail if it can't create all brick elements. Now, you do have some other options. You can have it create tet elements in between where it can't create bricks, or other methods such as Hex Dominant or Hexacore. So just some different options based on what type of elements you'd like it to allow the meshing method to create. So I'm going to set this to Hexacore for this particular part and just use the global size settings. And let's go ahead and generate the mesh just to see what we get. And what I suspect we'll get is that we'll get a nice hexahedral mesh on the outside and a great deal of brick elements for this part with relatively little effort. And if we look at it, that's exactly what we get. We get a nice looking uniform brick mesh. And if we wanted to, we could go ahead and use more local controls and get a even higher or more predominantly brick mesh using a smaller size elements. Okay, so just wrapping up, what we've talked about today, brick meshes are more efficient and more controllable. Again, we have a great more deep level of detail creating brick elements, and they're much more computationally efficient than using tet elements for the same resolution mesh sizing. Now, Ansys Workbench allows us many different options for generating a brick mesh, and the ease of use of Ansys Workbench makes generating these brick meshes more streamlined, simpler, and easier on the user. So a lot of different options here, and hopefully you guys can go ahead, go out there and use them on your parts. Now, unfortunately, we've run over, so what I'm going to do is any of the questions you guys submitted, I'll follow up with you via email afterwards. But thanks again for the input, and we appreciate you attending today, and hopefully you got a little bit out of it.